In this short video, I'll present our work on modeling and controlling hybrid wheel jumping robots. Firstly, why consider wheels on legged robots at all? Because they've become very popular in the recent literature with the animal with wheels, the Ascento robots, and the handle by Boston Dynamics. And wheels are good for locomotion on structured terrain, like roads and rails, whereas legs and legged locomotion is used when there is no such structure and there are obstacles to go through where wheels would get stuck. And putting wheels on legged robots allows them to operate in three sort of distinct modes, where one is use only the wheels and the legs then become active suspension, or stop the wheels, break the wheels, and then you can use them as regular quadrupeds or bipeds, or sort of the third mode, which uses both the wheels and the legs in a combined way to generate more dynamic motion, which is what we're going to be targeting with this paper. So we'll be looking at optimal control. And optimal control briefly finds trajectories, that is motion trajectories, states, controls, and in the case of locomotion, contact forces, that satisfy both the physics of the world, the dynamics, and the task constraints. And we'll be using a simpler template model in this paper to specify the dynamics of the system. So template models have been used to capture the essence of the dynamics without using the full rigid body dynamics. A very popular example is the spring-loaded inverted pendulum model, or the slip model here. Slip model can be used for generating walking and jumping motions, or we can stack two slip models in 3D and then generate motion in 3D. So we took a similar approach to hybrid wheel legged robots, taking a template model on the top left here in 2D and applying it to the simplest robot that has wheels and a leg. And the simplest robot is really just one leg. So we extended out to 3D and added two more wheels to make it a more complete robot. Our model, though, still remains in 2D. It can be thought of as based on the wheeled inverted pendulum model, which is a wheel with a point mass. The difference between that and our model is that we added a prismatic joint and a floating base, which allows for jumps to be solved for. And we will then use this template model in an optimal control in a transcription method to validate it on the robot in simulation. Here's what the pipeline looks like. On the right, we have the optimal control solution, so the full version here, which has the start and goal state, the task constraints, the dynamics, which are using the template model. State and control bounds, again, are task specific. And finally, we have the multi-phase formulation, which is used for jumping. So this is we pre-specify the duration of each of the phases. So we pre-takeoff, in the air, takeoff, and flight, and touchdown. So we pre-specify the duration of those phases, and we have the traditional constraints in the different phases. In the air, there is no ground force, and while on the ground, we have friction cone constraints as well as unilateral constraints, that is no pulling on the ground, as well as no slipping. So we took this transcription formulation and used it in the model predictive controller to execute it in simulation. So model predictive controller MPC is needed because the template model is by definition, by nature, not fully accurate. So the differences between the model and the actual robot are accounted for by MPC, which will solve a optimal control problem at every time step, then execute the first action, observe a state, and repeat this loop. It will also recede the horizon by counting how many states or how many states it needs for each of the phases, recede those automatically, and solve a different problem each time, starting with the previous solution for speed. We first demonstrate that we can swing up from driving forwards, and then subsequently balance on two wheels while upright, and while using the prismatic joint as well. The most dynamic motion is the jump over a gap, as shown in this video. Finally, we compared our approach to a PD controller on two different tasks. Both of them are driving forward. The first is drive forward a meter on flat ground, to which we added noise to the state space, to the state observations. And the second one is rough terrain locomotion, where the controllers do not know that there is rough terrain. The task there is drive forwards as far as the robot can with an episode that gets terminated after 5 seconds. So the results here show that MPC has a much lesser variability in performance in both tasks. So for noise, we measured how far away the robot is from the goal state. We tune both MPC and PD to have the same performance when there is no noise and when the terrain is completely flat. So in both cases, they had exact same performance at the start. As we increase the noise, we see that MPC is much better at getting to the goal state, at hitting the mark than the PD controller is. So the goal again is to drive forward a meter. In the rough terrain case, we measure two things. This is the mean absolute velocity of the angle of the angle of the robot, as well as the episode duration. So we terminated the episode when the robot falls over, and falls over means an angle of less than 85 degrees from the top. So MPC again shows a much less variability in performance. While both of them have an increased velocity due to the rough terrain, it takes more height for MPC to fall over, with it falling over after a height of 0.3 meters, and PD falling over already at 0.1 meters height. So this shows that even though both controllers were tuned at flat terrain with no noise, once noise is introduced or obstacles in the form of rough terrain are introduced, MPC has a much better performance than PD. In the future, we can extend the variable length wheel inverted pendulum model to 3D by stacking 2 or more, depending on the robot, to use on bipeds and quadrupeds. In conclusion, we developed a pipeline for the control of hybrid wheel jumping robots, the simplest hybrid wheel jumping robot, based on a simple template model. We demonstrated that even with a simple template model, we can already execute dynamic motions in simulations such as jumping. Those motions are discovered from the first principles of optimization. We show that we can use a simple, straightforward MPC formulation with a direct transcription method to execute those motions in simulation, and we compare them to a PD controller on rough terrain and with noise in state space.